Recording. Okay, so today we're going to talk about chapter 5. Right. Uh, okay, so chapter 5 is about the notion of subgroups, and it's kind of cool. So I think these three paragraphs are pretty good. Let G be a group and S a non-empty set of G. It may happen that the product of every pair of elements of S is in S. If it happens, we say that S is closed with respect to multiplication. Then it may happen that the inverse of every element of S is in S. In that case, we say that S is closed with respect to inverses. And then we have this picture that sums it up pretty well. When the operation of G is denoted by the symbol plus, the wording of these definitions must be adjusted. If the sum of every pair of elements of S is in S, we say that S is closed with respect to an addition. If the negative of every element of S is in S, then we say it's closed with respect to negatives. And if both of these things happen, where S is a subgroup of G. So essentially S being a subgroup means that every application of the operation of the group results in an element that is within the subset, and the same thing applies for the inverse. If those two conditions hold, then S is a subgroup of G. Then I have a bunch of examples, such as for the even integers, is a subgroup of additive group Z of the integers. And indeed, the sum of every two integers is an even integer, and the negative of any even integer is an even integer. So again, only two conditions that must hold. And then you may ask, why is this being called a group anyway in the word? And it's because a subgroup is also a group. So if G is a group and S is a subgroup of G, then S itself is a group. And well, you just have to reprove the associativity, the identity element, the inverse. Um, it's kind of like intuitive, but here's the explanation of why that's true. Um, and then we have another, and then we have a very cool example of functions, right? So the set of all real valued functions of a real variable. And then you can try to make the notion of summing them up. What does it mean to sum functions?
It means whatever APL defines that to mean.
Of course. And we're gonna check that by saying that yeah, this is the definition of plus we're gonna use. So the sum of two functions is the sum of their respective applications for the same number x. And then we're gonna say that f and g are s functions are equal if this holds for every number that we are looking for. And then we have to check the associativity, and there's also the whole neutral element. Um, and very okay. And the inverse of every function is given by this notation. There is a name for this type of manipulation of functions that we saw in the category theory book, Marinho. It was talking about the equality of functions, right? So, and I remember that using the outcome of the function application as the criteria for equality and things like that, there was a name for that, and I just don't remember. Do you?
Hmm. Nope.
But there is a name. You agree with that? That there is a name.
I would be surprised if there wasn't.
I thought you would remember the name. Well, let's do a quick function equality.
Isn't that a sheaf or something?
No, 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 no. Man, there was a thing. I'm almost opening the category 3 book here just to check that out. But there is a particular name for extensionality. There we go.
Ah, that. Okay.
Yeah, so this is the extension way of defining functional equality. Anyway, and we're trying to use the same principle for the inverse, and then you can do with many functions. and things like that. And there's also, yeah, this is actually pretty cool. In any group G, the one element subset, which is the subset with only the identity element, is a subgroup. It is closed with respect to multiplication because the identity element multiplied by itself is the identity element, which is in part of the subset, and it's closed with respect to inverses as well. So this is a subset. And then there's also the subset of the set being as itself. So we have now the notion of trivial subgroups, which is the, like, for example, the smallest and the largest possible subgroups of G. Um, yeah, now we're going to talk about the generators notion. Suppose G is a group of A, B, C are elements of G. Define S to be the subset of G, which contains all the possible products in any order with repetition of factors permitted. Thus, typical elements of S would be. Yeah, so this is because all possible products. So these are examples. It is easy to see that S is a subgroup of G. If two elements of S are multiplied together, they yield an element of S because of this definition here. And the inverse of any element of S is an element of S. For example, the product ABA and CB inverse of B, AC is this one, and the inverse of that is this. So it's called a subgroup. S is called a subgroup of G generated by A, B, and C. So it's essentially permutation on the seeds, and then you get the rest of it. That's the idea. That's the intuition of a generator. If A1 all the way to AN are any finite number of elements of G, we may define a subgroup generated by A1 all the way to AN in the same way. In particular, if A is a single element of G, we may consider the subgroup generated by A. This subgroup is designated by the symbol this with the angle brackets. It is called a cyclic subgroup of G, and A is called its generator. Note that that consists of all the possible products of A and inverse of A, for example, this thing. However, since the factors of inverse of A cancel factors of A, there is no need to consider products involving both of them side by side. Um, yeah, this is actually true, right? Because in any possible combination that you have, they will cancel each other out. Um, I guess. Well, I mean, but
Yeah, no,
that's
they will.
go on.
Because no, they will because like the only things you have are the identity, which is irrelevant for this kind of composition. A and the inverse of A, and if you have A and the inverse, they, as you said, they cancel out, which means you can remove it
Yeah,
from the overall from the final product.
yeah. If the operation of G is denoted by plus, the same definitions can be given by sums instead of products. Yeah, and this in the group of matrices. Yeah, and then I actually went to check this out, and essentially the way that you deduce this is like, what happens if I multiply the D matrix with itself and with its inverse, and then if you multiply by its inverse, you're gonna get I, and if you multiply it by, I think it's itself, you're gonna get B, and if you multiply B by D, I think you get D back again. So like
You
it's
get I actually. I think
uh, I don't remember. They only remember the rules that you're gonna multiply D by itself and by its inverse, and the itself and when multiplying by itself, aside from the cases that D being its own inverse, you're gonna get something else, and then you multiply D by B and B by D because matrix multiplications are commutative, and you're gonna get something else, and the same applies for A. But in the case of A, I think A times A
is
uh,
identity.
is identity, so that's why, and A inverse of A is also identity, so that's why there's only two things in here. And then you can check that in fact the entire group G of the table is generated by the two elements A and B, and this is essentially multiplying A and B and A, and then grabbing the outcomes of those products and multiplying by A again and by B again, and all those permutations are going to generate the entire table. If a group G is generated by a single element, we call G a cyclic group, which I have no intuition why the word chosen was cyclic, but It is what it is. And then we write like this. For example, the additive group Z6 is cyclic. And then what is the generator? So the Z6, I went to the previous chapters to check it out. This is the modulo 6 thing. So this is from 0 to 5. What is the generator of the Z6?
1 or
It
5. It's
is
actually, you can also say 5. That gives the same result because 5 is minus 1.
is 1 or 5.
For every modular group, it is going to be one, at least.
I guess that does make sense. Yeah,
For the
it is 1.
integers in general, it's going to be 1 actually.
For every modular groups on the integers.
And the reason why is because if you grab 1 and you do the sum with the modulo thing, with 1 you get 2, and then you have 2 plus 2 and 2 plus 1, and then eventually you're gonna like go through like the clock is gonna go all around. Anyway, every finite group G generated by one or more of its elements, obviously. A set of equations involving only generators and their inverses is called a set of defining equations of G for G if these equations completely determine the multiplication table of G. For example, let G be this group whose generators A and B satisfy these equations. These three equations do indeed determine the multiplication table of G. To see this, note first that the equation ABA and AB square allows us to switch powers of A with powers of B, bringing powers of A to the left and powers of B to the right. So for example, to find the product AB and AB square, we compute as follows. So because we know that BA is equal to AB square, we can do that. And then we can just sum those things up. And then this is going to be equal to B, right? Because A squared is equal to E, and B fourth is B3, B like cube of B, with another B, which means that all this entire thing is equal to B. All the entries in the table of G may be computed in the same fashion. When a group is determined by a set of generators and defining equations, its structure can be efficiently represented in a diagram called Cayley diagram. And as much as most diagrams that I'm aware in math, they are pretty, but I don't see I still don't know the reason that they must be drawn in this way. Well, I think it's because it makes them pretty, but that's kind of like a bad reason.
What do you mean by this way?
This way, you don't have necessarily to draw this particular diagram in this way. If you're willing to cross the arrows, like you have the arrows crossing each other, this could be
That's
drawn in
harder
many
to read.
million other ways.
Well, yes, but it's harder to read.
Um, but even if that's the case, why does the inner triangles are bigger? That would be in the same thing. So
Oh,
it's
you
the
can
same thing with the lattices, right? That I asked you the other day, actually the other year. I think it's 2024. Why are lattices drawn in the way that they are? And the answer we come up with at the time was because it looks pretty.
you could swap the triangles around, but it would still be the same figure. And there isn't really any other way to draw it if you're not willing to cross the arrows.
Oh, there is. The inner triangle could be bigger. That's what I'm saying.
That's just scaling.
No, but that's not scaling because you're not making the outer triangle bigger, just the smaller one.
Well, but if you do that, then there will be no room for the labels. And labels are conveying information, so you want them to be
Ah,
readable.
I don't buy that at all, Marinho. I think this triangle, inner triangle, could be bigger and still have labels. And the same thing applies for those other guys here, down here. Like this square could be bigger. Essentially, my question is that I think that there must be a rule, or at least a convention, that no book tells me. What are the conventions to draw these things? I think we identified already one about crossing the arrows, but aside from that, I really don't know. Okay, but that's pretty much it for the
Maybe
exercises.
the maybe the topologists would have a say on the matter.
Sure, but why are the other, like the non-topology books, not telling me that? If you like asterisk, if you want to understand why they are drawn this way, talk to the topology guys. Like, and this is not exclusive to this book. I think I already read or found the two books that I was reading for my masters that also were they had like these type of diagrams, and I couldn't like they are pretty, but I don't know how to draw them myself. So, and in the end, they didn't tell me. They didn't tell me why or how to draw them. Okay, so exercises. So which exercise you guys think we should go for?
Um, I think Group A is pretty interesting, and Group B is mostly kind of boring.
Wait, you say group A, you
The
mean recognizing
sections.
subgroups?
Yeah, section A is kind of interesting. Section B is kind of boring because it's kind of the same thing as A, um, but with functions,
Yeah, and they are more annoying. Okay, I
and they are
only
more
did the
annoying. Yeah.
one. A1 I did. Let me actually share the entire screen. There we go. So I actually have the first one here. And well, nothing too surprising, I would say. So it's essentially you have to prove that log A with A being the rationals and greater than zero, if this is a subgroup of this the G. And the way that I did that, I like again, it's the same thing that I complained last time. You have to understand, you have to exploit properties, algebraic properties of those things. So in the case of log, you have to remember that log A plus log B, if the base is the same, you can do a thing about it. And then because these are rationals, I essentially said that there must be an x and a y and a w and a z and things, and you can undo them with the sum with the product. And this fraction is definitely in rationals, which means that this log is in H. And to prove the inverse, you kind of also do you grab the minus and you put like inverse, and then you do the same trick with an x and a y, and then you reverse those as well. And this fraction is in rational, so this is also in H. So H is a subgroup of G. Uh, but that's kind of what I had patience to do, because the next example,
Oh, the next example is actually pretty easy though.
uh, it's the same thing, isn't it? Because this is in integers.
But it's not because
No, no, no.
the
When I
second
say the same
equation,
thing, I mean the strategy.
the strategy is the same, but this is not a subgroup actually because the second equation doesn't work for integers.
Yeah, because it's gonna be n time inverse of n, right? And that's gonna be 1 divided by n, and that's not in integers.
Yeah.
So H is not a subgroup. The 10 is kind of a thing, because I in my head there will be oops there will be something like 10 of x plus 10 of y, but that's not this. So what there must be some manipulation that allows us to put the plus inside of the tangent.
Uh, well, that's not really what the set requires. The set says, okay, x is a real number, but its tangent must be rational. Setting aside the whole constructivist thing that I have going on.
Yeah, no, but this is not what you said. Doesn't deny what I said. I'm saying that these being in rationals, oops, these being in
Okay,
rationals, we're gonna have 10 of x
actually,
plus 10 of y, no?
no, you're gonna have, okay, x plus y, but then x plus y, the tangent of that must be rational as well.
Ah, you're gonna have x plus y.
Well, yes, because the subgroup, the element is still x real, but
Ah,
its
okay,
tangent
no.
must be
Yeah,
rational.
no, I missed that part. You're right. There's gonna be x plus y, but then the tangent of x plus y must also be in rational. So again, you're gonna be able to use this formula and things like that.
Yeah,
Yeah,
and this is clearly not a subgroup.
clearly, elaborate.
Yes. Because what happens if that 10y 10x that you have at the bottom happens to be 1?
Then this becomes undefined, right?
Yeah.
And undefined is definitely not in here, so this is not a subgroup. Actually, this is a very good trick, Marinho, and I haven't thought of that. Of trying to like, instead of trying to, as I did with log, just trying to prove the thing as I go, try to immediately break it. And then the immediate break is what if this is one and this is one, this is not, then this is not a subgroup, done. That's easier, definitely easier. Okay, about groups A and B of exercises. Steve, do you want to say anything? Like, is there anything that you want to talk about?
Not about those two, no.
Okay, so Marinho, can we proceed A and B here?
Um, Real quick, just another note. A6, also not a subgroup because the identity is missing.
Identity is missing.
Yeah,
Interesting.
because the identity would be a 0, 0, right?
Yeah,
But
but
the
zero
quadrants
zero
of
doesn't
0,
fit
0,
this.
yeah, it doesn't fit. The quadrants of 0, 0 is 0, which is not greater than 0, so yeah.
Yeah, that makes sense. Okay, and then you do the kind of the same thing for functions, which is like very mechanic. But again, you have to have kind of know the tricks a little bit. So in these, the log ones, you have to know the tricks. In this one and in the sixth one, you can break them by doing what Marin just explained. But this is not really that like it's kind of boring, but nothing true like out of nowhere. And then we have the C, subgroups of abelian groups. So if H is all the elements that are in G, but they are their own inverses, prove that H is a subgroup of G. Okay, so actually for this one, my idea, um, my idea is the following. We say we need to check that X times a Y is within H, right? That's what we gotta have to do.
Yes, basically.
So how would you do that? You would say that you probably would swap one of the elements or both of the elements by their own inverses, right?
Uh, well, yeah, basically you have to prove that, that's not quite it actually. You have to prove that, okay, given two arbitrary elements from this age subgroup,
Yeah, so
you actually
X
have
and
to
Y.
prove, yeah, you know that they are each their own inverses, so you don't need to check if the inverses in the in the group because that's true by how it was constructed. But you need to check that xy is has an inverse in age, which means
Yeah, but this is no, what you said, right? So this, right? That's what you're talking.
yeah, you have to check that this is in age. And you can actually do that by exploiting the fact that these are abelian groups.
Done.
Because, yeah, it's basically just a very straightforward. I actually wrote this out in, like,
And just to explain
I was,
this is theorem three, right? So T3.
yeah, I was actually doing this on a text document because I actually, other than having to draw things, I'm actually pretty okay with solving these on text, and I came up with this.
Okay, let's read that. For an arbitrary and B in H, AB equals to BA, therefore ABAB is equal to ABBA, which is equal to AA, which is equal to E. Therefore, AB is in H by the definition of H. AB is in H.
Yeah, that basically proves that okay, given an arbitrary pair of elements from age, their product is actually in age because it is its
Yeah, no,
own
no, but that's
inverse as
only the
well.
first condition, right? We still have to talk about the inverse, and the inverse is this thing, right? That I did, I think.
Um, No, that second, like that chain of equations that after I say, okay, given that this is a billion, so AB equals BA, right? Then the sequence of equations after that proves that AB is its own inverse, and AB is clearly an element of G, which is its own inverse, so it must be in age, basically.
Wait, you're gonna have to repeat that. I don't see any inverses about the in the snippet there.
Well, ABAB, since it's a billion, it's the same as ABBA, right?
Yeah, sure.
And we know that B is its own inverse, so it cancels out. And we also know that A is its own inverse, so that also cancels out. So AB equals E, which is the identity element. So AB is in fact its own inverse as well.
Yeah, that is true. Okay, I see. I see. Let n be a fixed integer and let this be equals to that. Prove that H is a subgroup of G. So this is essentially saying that the exponent by a fixed integer is equal to the identity element for all elements in G. Is that a subgroup? To prove that, we would have to do, I don't know, xn times xn, and this is equal to x2n, right?
Um, I
But I
think it's
guess
easier to do
this is
x
e,
times
this is
x.
e, so this is e,
I think
isn't
it's
it?
actually easier to. Well, yes, but I think it's actually easier to go with proof by induction, where you say, okay, um, if n happens to be 0, then the only element is e, so that's done. If n is greater than 0, then x times xn minus 1 uh, must be e by definition, right? So that means that x has an inverse. And then using the same argument from from uh, from B1, which is B1 is the one about. Yeah, I actually wrote this down.
Yeah, I don't think you need induction to prove this one.
Yeah, not B1, C1 actually. But yeah, no, you can prove this. You can prove it that way. It's kind of annoying, but it's pretty straightforward actually.
Actually, maybe
No.
with the induction it's easier to prove the inverse though, because here's the thing. To prove the inverse, I have to prove that
Well, you can
xn.
use.
Oh, but
Yeah, you
this is
can
gonna
use
equal to
a.
the invert of this, and this is there. So yeah, proved.
Yeah, you can basically use the same, kind of the same argument from C1 to do the n times n minus x times x to the n minus 1 case. Or rather, you prove that, and then you use the one above for okay, what if there are multiple x's, right? And then you use the same logic used for one applies here. Well, a similar logic applies, right? Because it's not a self-inverse. It's the case of okay, if you multiply the thing by itself enough, eventually it's going to reach an inverse. So yeah, it's kind of interesting, but also kind of boring.
Wait, what you said at the end, I didn't get it. If you multiply the thing by itself enough, I don't get that. So when you say that, you mean what do you mean exactly? Multiplying by itself enough times?
Like let's say that n happens to be equal to 1, right?
Sure. So you're saying that
In
x
that
equals to e.
um, yeah, in that case x will be equal to e, and that's also the next easy case. But then if n equals 2, um, if n equals 2, that means that n x squared is e, but that means x is its own inverse, which means it's literally the same case as C1.
Yeah, this case is c1. I agree. But if n equals 3, oh, I see. This way of thinking, you that's why you got the induction thing.
Yeah.
Uh-huh. And then you're gonna say that this is equal to x times x squared, right? And x, and what are you gonna what are you gonna do from there?
Uh, well, you know that x has an inverse, which is kind of what you need for it to be a.
Oh, you're gonna say that x is equal to x squared is equal to x inverse.
Well, yes, x squared is x inverse, kind
X
of by
is
definition, right?
yes, yes.
Um, and if you happen to have um, if you happen to have multiple kinds of elements that eventually cancel out, like let's say you have an x and a y, that x to the n is equal to e, and have another element which is different from x, but also uh, let's call it y, but also y to the n is equal to e. That would also be
Yeah, it needs to be
in
n
the
there.
set as well, right? And to handle this case, then you have to do
Oops.
the argument. Yeah, because what happens if you have multiple elements that apply here? To handle this case, then you have to do the same argument from C1 above, where, okay, you can refactor the thing and then just, you can refactor the thing and then just, because it's abelian, right? You can group the x's and the y's together, and you know that, okay, this is in fact, these are in fact members of the group.
No, wait. No, 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 no. Let's talk. Go back in a step there. So we know that x times to the power of n is equal to e. But what are we gonna do about the y and to the same n here? We need to prove that this is also in H, right? That's all we need to do.
Oh,
Uh,
you can group the multiplications together, and then eventually you're going to multiply enough x's and enough y's that each one of them are going to be identities. So it's kind of the same thing.
yeah,
Yeah,
it's kind of the same
yeah,
thing.
that's what I don't follow. That's why I'm asking. So when you say we have two different numbers, right? We have an x and a y, and they're to the power of the same n. My question is
Yeah,
how you're going to group them together. And something happened with the.
because this is abelian, right? This is subgroups of abelian groups specifically. So we can use commutativity here.
Sure, but they are not the same thing. That's why I'm asking the question how they're going to cancel each other out. I don't know if my
They're
question
each
is
going to
making sense or not.
become identity individually.
I think the PDF viewer got screwed. Yeah, it did. What the fuck? Oh, there it is. Okay. Could you repeat that, Tivo?
But they are each going to become identity individually, like as you go multiplying more x's and more y's. And being abelian means you can reorder the factors in a way that groups them together.
Yeah, I think I'm. Wait.
Yeah,
No,
you
let's
went
just.
past it.
Yeah, okay. Yeah, but the PDF viewer is screwed. It's kind of like screwed. That's a new thing. I never seen that before. Um. Okay, there it is. Okay, I am still not following what you guys are saying about multiplying more things. But let's just continue. I can live without knowing the answer to this one. So is there any other exercise that you guys want to talk about in C?
Uh, Not really. These are mostly, like, other than 1 and 2, these are mostly kind of boring.
My mouse. Okay, that was weird. Man, let me try to reopen the book. I think something got really screwed. Yeah, it was screwed. I don't know what happened there. Okay, cool. Okay, so D, subgroups of arbitrary group. If H and K are subgroups of a subgroup G, prove that their intersection is also a subgroup. This to me is very intuitive, but how would we go to prove that?
Uh,
And this is also very intuitive, true.
if the intersection is a subgroup.
Yeah, if H and K are subgroups of G, prove that their intersection is the same. I think this is kind of like, it doesn't really matter. How should I say? Is a subgroup of a subgroup of the original group.
Oh, yes.
So this must be true. And this is the subgroup of the subgroup.
Well, you're kind of begging the question there, though.
No, I am just following the same principle. If a subgroup of a subgroup of the if that is a subgroup of the original group, then
Well,
this this just
Only
follows.
you kind of have
only
to prove that the intersection qualifies as a group, and then that follows. But I think you can sketch a proof by saying, okay, if there are elements in common between H and K, then for H and K to have preserved the group structure, then the inverses of each element must also be there, and
I
then
don't
you can
understand.
probably.
I don't understand what you said. Do you agree that this is a subgroup of H?
Well, you kind of have to prove that, actually.
No, no, sure,
Like,
sure. I It's just because let's say um, intersection always is gonna make this being a subgroup of its parents, no?
not necessarily. You have to prove that.
Not
you have to
necessarily.
prove that it is a subgroup, like that
I cannot
the
find the.
product of
Go on,
both
Tiff.
of two elements of this intersection does not escape the intersection.
Ah, that is the part that you have to prove. What Marinho said first, I didn't understand because this is a subgroup, and this is also a subgroup. We have something that is smaller than both of them, but that's the catch. You have to prove that applying the operation, you are still mapping the answer to the intersection, because you may be going to H or K in this case, right? By doing the operation,
Yeah,
and then that's the
basically.
problem. That's the
I
problem.
think you can. I think you can sketch a proof that goes kind of like this. So the identity element clearly must be there because the operation is the same between all three groups, right? Um,
Mm-hmm.
so that's a given, kinda. Um, if an element that's not the identity happens to be in there, then its inverse must also happens to be in the intersection, then its inverse must also be there because that means the element is in both H and K, right? But we know that H is a group and K is also a group, so if an element is in each of them, then its inverse must also be there, basically.
Yeah, but that doesn't prove it's in an intersection though. That only proves that it is in either in H or in K.
I don't know, it needs to be like for the elements to be in the intersection, it needs to be in both H and K, right?
Yeah,
So if the element is in both of them, and we know that both of them are groups because they are subgroups of a larger group G, right?
yeah, sure.
Then the inverse of that element must also be in both of them because otherwise they wouldn't be groups. You would be missing an inverse for an element.
Yeah, yeah, yeah. Actually, that is the case. That is the case.
Yeah, and then for the case of okay, let's actually apply the operation to two elements. If you take two elements from the intersection, then that means that each element must be in both groups H and K, right?
Mm-hmm.
But because H and K are both groups, then the result of applying the operation to those two elements, which are in the group, must also be in the group, and it must be in both of them. So the result is also in the intersection, and that's kind of how you would prove it, I guess.
Yeah. Yeah, 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 yeah. Okay. So yeah, and true is kind of the same principle. Let H and K be subgroups of G. Prove that if A is uh, contained in K, then H is a subgroup of K. So this is kind of like one rep, rep again. Uh,
Um, yeah, this one is a bit easier because you are told from the outset that they are both groups, right?
yeah. By the center of group G, we mean the set of all the elements of G which commute with every element of G. Yeah, so this holds. Prove that C is a subgroup of G. This means that it's abelian, no?
The center is abelian, yes, by definition.
Yeah. Uh, the center is abelian. And then we have to prove that C is a subgroup. Okay.
Yeah, I'm not sure how I would go about it, but this one got me thinking because this is actually an interesting case for me personally because I'm interested in quaternions, right?
Sure.
And quaternions are not commutative in the multiplication operation, right? But the normal complex numbers are kind of embedded in the quaternions, and that part has in fact a commutative multiplication. So yeah, this is kind of well, the not just the complex, but also the rationals are also embedded in the quaternions as well, and that's definitely has a commutative multiplication. So it's like, yeah, this is interesting for me, but I didn't spend much time looking at it. I was looking at the other sections more so than D3.
Okay, but how would we prove about this one? Because the elements of C are A's, which are part of G, right? So we would have to do something like, oh fuck.
Basically, you would have to prove that each element's inverse is also commutative with the rest of the elements of
But
G.
that's the second condition. The first condition is about the operation itself, right? So is this inside C? That is the question. What you said is also true. You have to check if this is in C, which in this case means that A inverse times X is equal to X times A net.
Yeah, basically.
Okay, so how would you go to prove this one?
Hmm, that's a good question. Let me think for a second. If
Uh, the first one is not that difficult because a times a being in C means that a squared times any x is equals x times a squared, and you can just rearrange the multiplication to show that that is true if the
that
product is true.
works, but what happens
Okay,
if you have an A and B which are different? Actually, I guess that also
That
holds
is
in
the
that case.
same. Yeah, it's the same pretty much.
wait, you said to rearrange this one, right, Tiv?
Yeah, you can expand the power and rearrange such that the a is on the right, and you can do that with a and b also trivially.
So you're gonna see, to check if this is true, we just exploit the property of C and say that, I don't know, maybe actually you have to do this in two steps, no? X. Let's manipulate this one. So this is gonna be AXA, and then you do it again with this right side using the other way around, and you're gonna get AAX, right?
Yeah, so that is on
Yeah,
C.
this one it is definitely in C. So first part it is doable. What about the second part, the inverse?
Hmm. Didn't we have a theorem earlier in the book about if an element? I might be misremembering that though.
Tell me, what are you trying to remember?
I think we may have seen a theorem related to this about, okay, if an element commutes, then its inverse must also commute, even if the group is not necessarily commutative as a whole.
Yeah, I don't remember having such theorem, no.
Because that's
Uh,
basically what we need for this case, right?
yeah,
No.
I would say. I would say so.
Hmm.
But there was an exercise where we proved that, actually, on page 40.
40. This one?
It's C1.
Yeah,
That's
definitely
not
not
that
page 40
page.
then.
Oh, it's marked page 40, chapter 4 on my book.
Chapter 4 you said though. Wait a moment.
Ah, so it's the page 40 of the book, not of the PDF, because there's a difference there.
Oh
Yeah,
yeah,
but
and
yeah, but
on
the
the
PDF
physical
does.
book.
Yeah, the book doesn't have the pages in the PDF version.
That is troublesome.
Okay, here. If A and B are in G and they commute, assuming that A and B commute, prove the following. A inverse of A and inverse of B also commute. Um, well, using that proof, I think we got it, but if you don't want to use that, what are you gonna do?
You would have to basically reprove it. Like there's no way around it. You have to prove that the inverse commutes.
You have to prove that the inverse commutes. Okay. Anyway, so let me remove these things. Okay. So, and then there is the same thing for the square as well. And then we talk about functions. Okay, anything special about D that you guys want to talk about?
Ah, other than one about the center, not really.
Okay. And then generators of groups. So list all the cyclic subgroups of Z10. So what are they? We know one is in here, right?
Right, the cyclic subgroup generated from 1 is just Z10 again, so that's definitely in there.
Yeah.
Um, actually, every other generator that's odd, that's not 5, is also equivalent to the whole group.
Why not
Um,
5?
of, because 5, you if you do 5 plus 5, that's actually 0. 5 is its own inverse.
Yeah, that makes sense. You need something to have like to get back to 1 essentially, right? You have to have at some point in the remainder 1 needs to reappear, and that it always happens with these 3. But with the 5 we go to 0, not to 1.
Yeah, so every odd number other than 5 is equivalent to the whole subgroup. 5 is just 0 and 5. There's no other elements in that cyclic subgroup. And then the even ones are also all equal to each other, and they just have the even numbers. So like, if you generate from 2, you get 2, 4, 6,
6,
8,
8.
and then you go back to 0, because this is mod 10, right?
Yeah.
And if you start with any other even number, you also get the same cycle, you just start at a different place.
And so these are the 4 cyclic subgroups of Z10. These 4.
And those are the interesting cases, yes. They are the ones that are like the ones that are just the full group are trivial, as the book calls them. The interesting ones are just the one generated from 5 and the one with the even numbers.
Show that Z10 is generated by 2 and 5. Well, this is very trivial, right? Because you just keep summing them up, and eventually you're going to generate everything from 0 to 9.
Yes, the critical case is where you do 2 plus 2 plus 2 minus plus 5, right? That gets you to 1, and
That
from
gets
there
you
you
to
can generate
1.
everything else.
Yeah, exactly. Yeah, okay, let me also write that down because just to be clear. The reason that what you said works is because that if you do 2 plus 2 plus 2 plus 5, this is 11, but when modding 10, this goes back to 1, and if you have a 1, you have everything you need because of this exercise here.
Yeah.
Cool. Describe the subgroup Z12 generated by 6 and 9, same thing. Describe the subgroup of Z generated by 10 and 15. These are all the integers, right?
No, actually. Oh, actually, z is all the integers, but z generated by 10 and 15 is just the multiples of 5, actually.
Yeah, this actually starts to be like, what does it say? Greatest uh, GD something from school. Do you remember?
GCD, the
Yeah,
greatest common divider.
exactly. These things start to kind of like feel like that.
Yeah, the subgroup generated by 6 and 9 on 3 is actually just the multiples of 3. And yeah, this on 4 is just the multiples of 5 because you have the inverses as well, right? So you do minus 10 plus 15, that's 5, and that's like the smallest integer you can get this way.
Man, that's kind of weird. When I use my finger instead of the pen, the orientation is completely reversed for horizontal stuff. So now I'm
Hmm,
putting my finger to the right, but it's going to the left.
that's weird.
Yeah, but with the pen, that doesn't happen. Anyway, so show that, oops, show that Z2 Cartesian Z3 is a cyclic group.
We skipped 5, but that one is pretty easy because 5 plus 5 plus 5 is 15, minus 7, that's minus 14, so that's 1. That's pretty trivial, but it's interesting to note.
Wait, show that integer is generated by 5 and 7.
Yeah,
You said what? 5 plus 5 plus 5 minus 7 two times?
yeah, that
But
gets you 1.
but you're doing using a minus. How does that work?
Well, when you generate a group, you have access to the inverses as well.
Ah, I see. You're doing plus with the net with the inverse.
Yeah,
Okay, so show that Z2, Z3. Okay, so these are essentially like what? These are particular pairs, right? So this is what? 0 and 1, 0, 1, 0, and then this is 0, 1, and 2. So if we make this thing, it's asking us to show that this is a cyclic group.
yeah, you need to pick a pair, a single pair that generates the entire group, basically.
Isn't that
Um,
like 1, 1 or whatever?
yeah, it's 1 1. For both these and for the 3 4 case as well, 1 1 works.
And the other one doesn't work because you have 0, 1, 0, 1, 2, and 3. So why
Yeah,
these cannot be a cyclic group?
this doesn't work because if you start from 1 1, um, one cycle is exactly half of the other, so you'll never get the combinations where the parity is different between them. So like from 0 0 you go to 1 1, so both parts of the pair are odd, right? And then from there you go to 0 2 and both are even, and then you go to 1 3 and then you're back to 0 0. So you never get the combinations where you have like 1 2 or 2 1, you see, where the parity is different between each half of the pair.
Wait, to do the combinations that you're talking about, you have to like you said start to 0 from 0 0, right? So you start from 0 0.
Yeah, then you keep adding 1 1 to see that it actually doesn't work, basically. You only get half the pairs.
Wait, so you're telling me to add 1 1 to both of them here.
Yeah.
So that's going to give us 1 1. And what
Yeah,
do I
if
do
you
next?
you just keep doing it and you note which pairs you get. So we have 0 0, that's the starting point. We have 1 1, that's the generator that we picked, right?
Yeah.
But then the next element after that is actually 0 2
Why?
because Because 1 plus 1 is 2, but this is mod 2, so that's equal to 0, you see?
Um, wait. I got what you said about the 1 plus 1 equals true, but true is mod true, so you go back to 0. But this guy here, this is on the mod
That
4 still, right?
That's on the mod 4, yes.
And then we
Then
get
if
1,
you do,
3,
you go to 1, 3, but then if you do 1, 1 again, you are back to 0,
0,
0
0,
now.
0. Yeah, you're never gonna get the combination. Yeah, never gonna get these in this position. And things like that, right?
It is
Yeah,
good
you're
to
not.
note that you can only set the starting point at 0, 0 because the element we have is 1, 1, and 1, 1 plus its inverse is 0, 0. Like the actual starting point should be 1, 1, and then you get to 0, 0 by
Ah, I see, I
going
see.
around.
You're right, you're right, you're right.
But
We
yes,
need to start
the
with the
rest is.
generator. But in this case, we're gonna get there eventually, as you said right now. Okay.
But we have the inverse of the generator, so we can trivially get 0, 0, no matter what we get,
Oh,
what we pick as.
in this case, yes, but it's not in general that you can start with 0, 0.
Okay, let's speed this up because it's already 56 minutes. Okay, so anything else about E, boys?
Um, H is kinda interesting, but there's not much to say about it other than I had fun doing it.
Suppose a group G is generated by two elements, A and B. If A, B equals BA, prove that G is abelian.
Yeah,
You
that's
can,
kind of
but,
fun
well,
because the trick is because every element is generated from A and B, that means every element can be factored into A's and B's, and you know that A and B commute, so you can factor it, commute the A's and B's, and then refactor it back to the original form, but backwards.
yeah, like, if you have the two generators commute, it's abelian. Like, I know this is not a proof, but to me that's kind of like a consequence of the statement. If the generators are they commute, then it is abelian. Yeah, sure. Okay, F. Groups determined by generators and defining equations. Let G be the group whose generators satisfy these equations. Write the table of G. So which table are we talking about? Are we talking about the table like the matrices?
Yeah.
No, that's gonna be boring as fuck.
Yeah, those are kind of boring. Although F3 is kind of interesting because it's about quaternions. But yeah,
Let G be the group whose generators satisfy. Yeah, you essentially multiply them to make the table, and you use the equations to simplify them further.
yeah. Basically, E is one, A is I, B is J, and BA is well, B is J, and from I and J you can get K. So yeah, that's and from I, J, or K you can get -1, and yeah, that's basically just the quaternions, the unit quaternions, right?
Wait, you're talking about the matrices again?
No, I'm talking about F3.
But there's no K here. That's why I'm asking. Where are those extra letters coming from?
No, no, I'm talking. This is called the quaternion group because if you translate these to quaternions, A is just the number one, or rather, E is just the number one because that's the multiplicative identity, right? Um, A is I, like the imaginary unit I, and then B is the imaginary unit J, and then
Ah, okay, I see. We are mapping these coordinates to another set of coordinates. And then, yeah, sure.
yeah, and then AB is Uh, AB is well, BA. I actually figured that one out. Is JI, which is minus K. Um, and from I, J, and minus K, you can get minus A, minus J, K, and -1, basically. And those should map to the generators that are in the set there in some way.
Cool. and then Cayley diagram. So this is essentially like how do you make one. So I think this is important to read. So a Cayley diagram consists of points joined by arrows. There is one point for every element of the group. The arrows represent the result of multiplying by a generator. So and then we have different arrows. So if you are a dotted arrow, then this means multiplying by A. And if you are like a solid arrow, this means multiplying by B. However, there is a catch because it is also a convention that if A squared equals to E, hence A is equal to its own inverse, then no arrowhead is used, which I don't know if I like it because I don't see a reason to denote this fact in the diagram. But sure, for if A equals the inverse of A, then multiplying by A is the same as multiplying by the inverse of A. The Cayley diagram of a group contains the same information as the group's table, but you can walk through it, which is cool, right? So if you have an AB square and you want to know how to get to E, you just have to multiply by a B and then multiply by an A, or multiply by an inverse of A, and you get to an E. And that's cool.
Yeah, yeah. This is basically a graph representation of the tables that we've seen earlier. I think this is actually nicer.
Um, I mean, yeah, I think it is nicer. Uh, okay, so let's imagine this example AB times AB squared. And this path leads to B, hence there must be, like, if you multiply, we can actually do this example like right now. If you start on an A, so here, and you multiply by a B, you go here, AB, then you multiply by an A again, so you go to B squared, then you multiply by B two times, so bam and bam, so that's equal to B, and that's it. Okay, that probably this gets pretty um, unmanageable pretty quickly because this is assuming that you only have two generators, right? Which is not may not be the case.
Yeah, this can probably get pretty big.
Yeah, so a point and arrow diagram is the Cayley diagram of a group if and only if it has the following two properties. For each point x in generator A, there is an exactly one A arrow starting from x and exactly one A arrow ending at x. So there are limitations, right? So you cannot have there is exactly one A arrow starting at x and exactly one A arrow ending at x. Yeah, okay. And B, furthermore, at most one arrow goes from x to any other point y. If two different paths starting at x leads to the same destination, then these two paths starting at any point y lead to the same destination. Cayley diagrams are a useful way to find new groups. So then the exercise is essentially writing the equations that construct that can be represented with these diagrams. So write the table of the groups. So my understanding how you solve it is uh, you probably do give names to each of the points, and then I don't know. You kind of create a table out of that, and you check the ones that must be the same, and then I don't know A B C D A B C D, and then
Oh, you can just call a point E and then start walking around the
yeah
diagram
yeah
using the
eventually one of
rules.
those will have to be E, right? So, because you know that's true.
Any of them can be E, according to the exercise.
Um, yeah. So let's say that this is B. Let's say this is A. Let's say that this is AB, maybe, or BA, I guess. And then you write that down. That's kind of what I thought. But the problem is that for things like these, that's gonna be boring, huh? What do you guys say?
Eh, yeah, this is kind of boring, honestly. Like, it's interesting to know the diagrams and how they relate to the tables, but generating one from the other is just pretty mechanical.
Yeah. And then we go back to the example of the coding theory, which essentially explains matrix multiplication and vector multiplication with matrices. And then there's a parity matrix, which is kind of cool.
It is very much tangential, but Wikipedia has a very cute interactive diagram for quaternions.
Interactive. It's not loading for me at all.
That is fun. It works on Firefox for me. But
Cool.
it's like a diagram and you can click to highlight stuff. It's
Ah, so it is
whatever.
interactive. Nice. Okay, and then we
See, man.
can signify the whole parity checks with a bunch of vectors. So the last two equations show that the word blah 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 is a code word if and only if this is orthogonal to both rows of the matrix this. H is called the parity check matrix of the code C1. This conclusion may be stated as a theorem. Let H be a parity check matrix of the code C. Our word X in that is a code word if and only if it parity checks. And the parity checking can be encoded as matrix multiplication. And then we have essentially to rewrite a bunch of stuff that we did before, but in matrix form. So find the generator matrix G2 and the parity check matrix H2. I have a question, which is the following. Yeah, so these two sentences here, for example, if C1 is the code given on page 34, its generator matrix is this because you may check that all 8 code words of C1 are sums of the rows of G1. So are they saying that if we sum 2 by 2 rows of this, we're going to get all of the all 8 code words of that one?
It's saying that you can get any of the all of the words there by summing any of the. Oh, you can factor any of the rows there into sums of those rows, basically.
Yeah, but you are always summing them up 2 by 2 only.
Not necessarily. You can sum more than one.
More than
You
two, you
can.
mean?
Oh yeah,
Yeah,
more
but
than two.
summing rows more than 2 can be encoded and always like sum those 2, grab the result of that, sum those 2, and keep going, right?
Yeah.
Oh yes, naturally.
Yeah, I never seen this before of like a code word mechanism that is based on a matrix that you actually just sum the rows. I never done that before, even in college. And I also never did parity checking with matrices in college, but this was kind of trivial because it's just some representational matter. How are you going to represent the parity? You can represent them as two vectors or a matrix. That's fine. Okay, so about this one, which section is this? G, no, H.
Age.
Anything
And the
about it?
Lex. Not really. Oh, hello, Ace.
Hello, Ace. Okay, Tevo, do you want to talk anything about it? Is there anything interesting to you about this exercise?
Not really. No.
Okay, I'm gonna finish the recording.